Okay, now having read a little bit about CMOS static characteristics and as well as the MOSFET capacitance, now we will try and learn about the CMOS inverter transient response. Okay, now so if you see here, this is a waveform which we have discussed earlier also. So this is the input which is changing. It is a non-ideal input. So it is not a perfect square wave. So this we are assuming this input is coming from the previous stage. Okay, for the one inverter is being driven by some other inverter. So this is the output of the first inverter. This is the output of the second inverter. So for the propagation delay, you take from 50% value to 50%. So this is known as to propagation delay high to low. Okay. Now high to low, we need to remember it is always referred with respect to the output and not referred with respect to the input. Okay, so many people do make these mistakes in the exam also. So always do remember, when we say propagation delay high to low and low to high, it is always with respect to the output. Okay, not with respect to the input. Okay, so this is the propagation delays, right? Low to high and high to low. And also this figure of merit also is used, which is actually gives the same performance parameter, which indicates the speed of the circuit, which is known as the rise time and the fall time. Again, this is again with respect to the output. Okay, a fall time is from 90% to 10%, and rise and the rise time will be from 10% to 90% of the total output swing which is there. Okay, so these parameters also sometimes used in, many people do refer to rise time and fall time also. Okay, whether MOS capacitance have a variation with respect to process? Yeah, it will have, like especially when we design a circuit in actual circuit which requires to be fabricated. Then the manufacturer provides for each MOSFET. So for NMOS, okay, he provides an NMOS low, NMOS normal, and NMOS fast. Okay, so three MOSFETs he would give, right? So NMOS low indicates that capacitor, that particular MOS is in the worst case fabrication process, worst case MOSFETs because of the process variation, and for NMOS fast indicates the best MOSFET which has been fabricated. So when you design a circuit, you do this 3 into 3 into 3 matrix. Okay, what it means is you will do the circuit with normal MOSFETs, slow MOSFETs, and fast MOSFETs. Also you will do for VDD 90% VDD and 110% VDD. That means 10% of VDD variations, and then you will do for temperature also. You will do it at room temperature as well as in 0 degree and 100 degree. That depends on the actual applications. If you are going for military applications, then probably 100, 110 or 150 something like that, and minus 10. If you are going for a commercial application, then from 0 to 100 would be good enough, right? So you have three different parameters now: NMOS, slow, normal, and fast. Then you have three VDDs, right? Nominal VDD, minus 10% and plus 10%, and then you have the what is the third thing? Temperature, process, and temperature, right? So you have three different room temperature. So in all, then you make a matrix, then there will be a total 27 different combinations, and in each of these combinations you should clear the minimum set parameter. Okay, whatever you might have made an amplifier which operates in a particular, which has a certain bandwidth and gain. So the bandwidth and gain should be above the minimum value in all these 27 corners. Okay, how to quantify slow or fast process? What parameters? While they are fabricating from the fabrication lab itself, right? We don't set each values. They summarize the entire thing. what is the worst device which might get fabricated because of the fabrication variation in the fabrication issues. The fab lab itself, they will say this is my worst device, which they generally call it as slow, and because of the fabrication process variation, because of the this is the best device which will come, so they call it as fast. And so when we take the library of a fab lab, so there will be 3 MOSFETs available there. Okay, generally if you are doing it like we are doing it for in LT Spice, we just have the single NMOS, whereas if you are doing it for a fab lab, actual fab lab, in which you have an MOU or something where finally you are going to fabricate the chip, then they will give all the 3 kind of devices, like NMOS fast, NMOS slow, and NMOS, like in GDPK also, I think all the 3 devices is available here if you are doing the general purpose, because when you go to that simulation setup in Cadence, you have that SS and such kind of setups available, so which will select the necessary model file accordingly, the slow and the fast models. Okay, so in LT Spice we are using a single normal file. Okay, yeah, tell me.
I have a question.
Yeah, yeah.
So when we talk about the load capacitance for an inverter, it should be, when we say load capacitance is such, so it should be basically based on the fan out, or like the input capacitance
Yeah.
of the device that is being driven by this device, right?
Yeah, correct.
So in that way, if I say load capacitance, so let's say when we say an inverter is driving another inverter,
Yeah,
so in that way, the load capacitance would be if the NMOS source is grounded. In that case, it could be something like the gate to body and the gate to source capacitance. Is this correct?
yeah. Yeah, I'll just those slides are coming up. Okay, if still it's not clear, just remind me. Okay. Okay, so today we are going to try and analyze what is going to be the propagation delay of an inverter. So the first assumption what we are going to make out here is right, that the input is going to be a perfect wave. Okay. Otherwise it would make hand calculations very complex. So we are going to make one assumption that the input is a perfect square wave, and then accordingly try to find the propagation delay from high to low and low to high. Okay, excuse me. So this is a square input being applied. So this is our inverter. So all these capacitances are there, and when it is driving an next stage of amplifier, so there could be n number of MOSFETs which it is driving. So this is one inverter. So you will find the net gate capacitance comes as an load capacitance. Excuse me. This is the interconnect capacitance, and at this node will have gate to drain here, and then gate to body and gate to body. So these 4 at this node you will have 4 intrinsic capacitance. Okay, this is intrinsic because this is within this capacitance. We don't have any control over this. This will be there in any case. This depends on how we have done the layout, and this depends on the fan out. Okay, is it okay now? So this is the total net capacitance available at this node. Okay, so CL is actually a sum total of this intrinsic capacitance plus interconnect capacitance plus the gate capacitance. Okay, so this is the gate capacitance here. Right now there are 3 methods to calculate the inverter delay. Right, one is known as the average current model, differential equation model, and first order RC model. Okay, so all of them are pretty simple. We'll see how it is done. Right, so in the average current model, if you see the capacitance is Q by V, right? So I is dQ by dt, or I can write it as C dV by dt, right? So if I take an DC kind of model here, so delta V, okay, delta V is the total variation in the voltage, and delta t is the time taken for change of that voltage, and I take it as an average current during this process. Okay, like so for example, when the output voltage is going from high to low, so I have C load. C load is fixed, right? Whereas this voltage as from VOH to 50% voltage. Okay, so this changes from here. I average high to low, right? So initially there will be some when it is just switch. It is when the output is being from high, when the NMOS is just switched on, there will be some I, and when it has reached 50%, there will be one more I. So you take an average of those two currents out here. So if I see here, so then I can put these values. This will be generally VDD, this will be VDD by 2. So this entire thing will become VDD by 2, right? So now we just have to compute the I average. Is this concept clear to all of you? Yeah, okay. Keep writing something in the chat box so that I know. Okay, okay. So now if you see here, so to find out an I average, okay, I take half of this current plus this current. So initially now the output is high, the NMOS has just switched on. So at that point of time, right, so the current will be a Kn dash W by L and a Kn dash by 2 W by L VDD minus VT the square, VTN. Okay, it's VTN here, VTN square, right? So because the transistor will be in saturation, VDS in that case is total VDD, right? So it will obviously it will be in saturation. Okay, so that is one current. What about the second current? Okay, whether the transistor will be in saturation or whether it will be in linear region. So we need to see and then accordingly use the current equation. The transistor might be in saturation or the transistor could be in a linear region also, right? For example, if I am using an 45 nanometer technology, right? So the VT is around 0.6 value. Okay, if it is VT is 0.6 and voltage is 1 volt. Okay, so can anybody guess what would at 50% will it be in saturation or it will be in linear region? VDD is 1 volt for 45 nanometer and VTH is 0.6 volt. Right. So what is the gate? What is the gate voltage? If you see the gate voltage is, yeah, it will be in saturation, right? Correct. Because VT is 1 minus 0.6, 0.4 volt, whereas half VDD is 0.5 volt, right? At the output, VDS will be 0.5 volt because 1 volt is the VDD. So I will have a 0.5 volt across the drain. So it will be in saturation, whereas this is 0.4 volt overdrive voltage, 1 volt minus VT, that is 0.4 volt, right? Whereas if I talk about 180 nanometer technology, right, it is 1.8 volt and VD is around 0.7 volt. Then I will have 1.8 minus 0.7, that is the at the between the gate and the source. Okay, it will be 1.8 minus 0.7. Which is around 1.1, whereas VDS for 50% will be only 0.9 volt, so it will be in linear. So depending on what circuit and what voltage and what technology you are using, the second current could be either for 180 nanometer it will be in linear, for 45 nanometer 1 volt it will be in saturation. So depending on that you need to use one of these equations, right? And then you find the average value. Okay, those are same thing holds good for the low to high also. You need to use the PMOS current equations, right? It will be when it is about to get when initially the output is low and PMOS is switched on, it will be in saturation, and subsequently at 50%, whether it will be in saturation or whether it is in linear, that depends on the actual technology and the VDD which we are using. Okay, so this is how we use the average current model. Yeah, tell me.
Sir, in the I average HL equation,
Yeah.
just before that it is written that the high to low transition average current can be calculated by using the current values at the beginning and at the end of the transition.
Yeah.
So for high to low output transition, the input would be low to high, right? So in that way, beginning of the transition will start when V in would be VOH. So the first term is basically representing the beginning of the transition.
Yeah,
Now,
yeah.
the second term, how could you say that this is the end of the transition?
Because we are for us to compute the propagation delay, once we reached 50%, we have reached the target voltage, so that becomes end of transition. Yeah, for this particular case, although it will still further go low or high, but for our computation, that is the end of the transition, right? It is given here, V out is equal to 50%. That is our target value. Okay, is it okay? Yeah, okay. So you can expect these kind of small calculations in your midterm. Okay. Exam. Okay. Now there is the second method is a differential equation model. Okay. In this, if you see here, now if you see here, C is Q by V and I is equal to C dV by dt, or if I put in a dt, it is C into dV by I. So you are integrating this time for a value of V out to V out minus now here again there we are taking two different conditions here, right? Okay, here now the output is going from high to low. Okay, both of them we are telling till this region it is going to remain in saturation. From here to here it is going to be in a linear region. Okay, so what is the point till which it will be in saturation? Okay, till VOH minus VTN, till this voltage comes to VOH minus VTN, this will be in saturation. From here to here it will be in linear region. NMOS will be in, sir, when V in is equal to VOL, NMOS will be in cutoff. Yeah, it will almost reach an cutoff. Yeah, correct. So this is the equation which these are the two regions we are defining here. So here we are going to use the linear equation, and here we are going to use the saturation equation, right? So from V out, that is VDD, to VOH minus VTN, we are using this saturation equation, Vn minus Vtn the whole square here, and we integrate it. So you get this value 2 V out Kn VOH minus Vtn square, right? And then from here to here again I use the linear region. Okay, so I use this equation of linear region here, and I put this VTON to 50%. So this is again I am using what there. So okay. So we do this integration over this region, so you get the second time, and then you add both these times together, so you will get the total propagation delay, right? So this we are doing, just integrating these values. Okay, these might look very complicated as of now because the variables have not been specified. The moment you put the variables, these equations will look simple. Okay, so the way these two regions, now we are assuming that it will be in linear in this region, and then here it will be in right in the saturation region. So we have divided this curve into two different paths, and then we have done this integration to get these two times, and then we add these two times to get, now it is up to 50% only, right? From here up to 50% only. So here it is going to be in saturation, and here it is going to be in the linear region. Okay, so if you assume that the entire thing it is going to be in saturation region, then that also can be done. So then the total variation which you will find is only 10% variation. You can integrate from VDD to VDD by 2, and you can use the saturation equation itself here, right? So you can do this also straight away. So from VDD to VDD by 2, and then you are using the saturation equation here instead of the linear equation. You can straight away use the saturation equation, so you will get the final answer and a simplified version of it. Okay, so the variation is only 10%. So instead of dividing these two curves into two different regions, we can also assume that during this entire process it is going to be in saturation region. So you will get this particular equation. Okay, so this is one more method of computing the total delay. Same thing can be used to compute a low to high also. Okay. Now this is
all the transient cases,
yeah.
we should consider that all the currents that are flowing are supplied by the capacitor, right? Otherwise, there would be no current flow.
Uh, uh,
Capacitance only.
yeah, load capacitance, correct. Either the load capacitance is being charged, or from going from high to low, the current is coming from the discharging current. Yeah, sure. Okay. This is again in case I'm just mention, I put this slide so that you know. So in case we are talking about an velocity saturation case for low channel devices, in that case we know that the equation gets changed, right? So instead of VD sat becomes LV sat by mu n. This we saw the second order equations, right? So I've just put this slide for you to know that the equation would slightly change, and it will get restricted. The currents will get restricted because of the VD sat equation. So you can use this equation for velocity saturated devices. Okay. And there is a very simplest method which is known as RC delay model. Okay, in this what we are assuming that the PMOS has got an channel resistance which is represented as RP. So this capacitance is going to be get charged, right? And we know the capacitance equation is given by V is equal to VDD into 1 minus e to the power of. So in this equation, if you see here, if you put T is equal to 0, so this becomes 1 minus 1, the capacitance voltage will be 0. And if you put T is equal to infinity out here, okay, right, then this becomes 0, then V is equal to VDD. Like at T is equal to infinity, this capacitance will get charged to VDD, and at T is equal to 0, it is 0. So this is how a capacitance voltage is written, and this is the time constant for an capacitance, right? RP and C. So if you have an greater R or greater C, it will take that much more time for this capacitance to get charged. So that is the reason it is there in the denominator, and RP is known as the time constant, right? Now we want to find out what is the time taken for this capacitance to get charged to VDD by 2. So I put here 50%, that is VDD by 2. I put a VDD out here. So this equation becomes a half of e to the power of T low to high, and then you take a log and you compute, so you will get 0.69 RP C load. So this is a simplified version. Similarly, for an NMOS, it will become Rn out here, right? Now, what is the value of RP? C load depends on the loads upon the fan out also. So what about RP and Rn? So they are generally empirical values. They have been, this is the general formula which we use to compute Rn and RP, which is 12.5 divided by W by Ln and W by Lp for RP. So this is an empirical value. So this is you can model this PMOS as an RP whose value is given by this equation. Okay, so it has been found that these particular RP and Rn values, once you do the computation using these formulas or these formulas, they will approximately come to be the same for these technology nodes. Okay, and that is the reason we can use these values of Rn and RP. Okay, so this is empirical values. No, empirical values means through what experimental observations. Okay, these formulas have been derived. Okay, so this is the third method of computing the delay. So these are the three various methods which you should know. Okay. So that is important from your exam point of view also. Okay, these three methods. Okay. Now if you see here, this is an straightforward curves which you can see that beta is Wp by Wl Wn as long as with L being same for both the no, PMOS and the NMOS. So if you see here, if you keep increasing beta, the low to high, TP high to, low to high will keep decreasing, because PMOS is stronger, so it will get the output will get charged faster, but it will increase the if NMOS is becoming weaker, you will find this is increasing, right? From, if you keep increasing beta from low to high to low, okay, this is going to increase, right? So if you take an beta is WP by WN, for L being constant for both of them. Okay, so if you see, if you increase beta, that means you are making a PMOS stronger. So if you make if you keep NMOS weak and PMOS if you make stronger, so the rise time will decrease. That means PMOS is stronger here, so this will keep this delay of low to high is going to decrease, whereas this is going to increase. So the optimum value somewhere here is around 2.5, right? So for VTC we saw it is 2.5, and even for the speed, this again for long channel, it is around 2.5. So for long channel devices, so generally 2.5. We said we are going to use an 2. Okay, so between 2 and 2.4 it will make a small difference. Okay, so that is okay. Yeah, in RC delay model we have considered RP and RN assuming linear region of operation. Will not the MOS be saturation region as no, in RC delay model, okay, this is an empirical value throughout the region. This is an average resistance of the PMOS, you can call it that way. Okay, here it says yeah, obviously the PMOS has gotten higher resistance, right? So here if you see in these equations, okay, good that you brought out, RP is greater, so accordingly if you have to keep the rise time and fall time constant, even in this model if you see here, you have to keep the W by L ratio of P greater than around 2.5 times, right? You will have to keep it high to keep the rise time and the fall time constant. Devdit, is it okay? Gets less than. Right, if you see here Rn is lower, Rp is greater. Okay, that is because of the mobility issue. Even in the other equations also, if you try to solve that, you will get the same, because the Kn is different here, right? For each of it is Kn here, so here it is Kn, right? So it will become Kp. So if you have to offset Kn and Kp, right? So the widths have to be accordingly modified. So same in this model also, Rn PMOS strong is, yeah, PMOS strong means W by L is more as compared to the NMOS. Okay, that's what. Yeah. Okay. So in this for all these models, you will have to ensure that the width of the PMOS is kept around 2.5 times. In all the whatever way you derive it, you will reach the same conclusion, that the widths of the PMOS have to be kept at least 2.5 times, around 2 to 2.5 times the width of the NMOS, to get an symmetrical rise time and fall time. Okay, or symmetrical propagation delay. Okay. Yeah. Now if you see the delay of a CMOS inverter, right? If I go with the third model which we just saw here, right? In this model, okay, we are going to use this model out here. So if I write it as R equivalent, and the capacitance I am going to divide it into two. One is known as C int. Okay, int doesn't mean interconnect, it means the intrinsic capacitance here. It is not interconnect. C external means the interconnect plus the load capacitance, right? So C int here. So now if I take out the C int common here, okay, C internal out here, 0.69 R equivalent and C internal. Now I can write it as an TPO, right? So what is TPO is 0.69 R equivalent C internal. Right now, this is not an no, if you see here, this is an technology dependent component, and it is because of the intrinsic capacitances which is associated with the inverter, and it is not it has nothing to do with the loads which is connected here. So this is the minimum delay which will be there as such. Okay, this will be there in the circuit. Okay. Yeah. Okay. Am I audible? There was some internet issue. Okay. So if you see here, TP0 is equal to 0.69 R equivalent internal. This is purely technology dependent. It doesn't no, it will be there irrespective, even if there is no load connected, this much delay will be there. Also, important thing to note out here is this is not dependent on the width of the transistors also, because if you see, if you increase the width of the transistor, right, then the capacitance will increase and the resistance will decrease, right. If you decrease the width of the transistor, then the resistance will go up and capacitance will come down, right. So this TPO is known as the intrinsic or unloaded delay, and it is independent of the load as well as the sizing of that the inverter also. Is this aspect clear to all of you, right? This TPO. Okay. So and then if you is it clear to all of you? Can somebody confirm? Yeah. Okay. How independent of W? Yeah, that's what. Why it is independent of W is, see, this is 0.69 R equivalent into C intrinsic. Okay, C intrinsic is the capacitance of the inverter itself, not the load capacitance. If I increase W, R equivalent will come down and C will proportionately go up. So they are like, if you see R equivalent formula, W is in the denominator, and C intrinsic, you will see W is in the numerator, right, the capacitance. So they get cancelled each other. So that is why it is independent of the transistor sizing also. Is it okay, Pooja? Yeah, okay. So this is known as the intrinsic capacitance, and then you have 1 plus C external divided by C. So because we have taken C in, okay. So this is the equation. Okay. Now if you see here, now if you keep increasing the size of the transistor by making C int, right, C int now much larger than C external, right, then the delay will keep coming down, and then it will reach a value which is equal to TP0. This is the intrinsic delay, right. So if you keep increasing the size of the transistor, right, if you keep increasing the size of the transistor, TPO doesn't change. Okay, so TPO doesn't change, but then the total delay is TPO plus C external by C internal. Now if you keep increasing the size of the transistors of the inverter to a large extent, that is S here, you will find that the C int becomes now the major dominating one. So that offsets the effect of C external, and then this delay will come to TP0. Is it okay? Yeah. Am I audible now? There was some net switching again. So, sir, is the determining of fan out of a particular, I mean, is there is a trade off, right? Yeah, okay, let me repeat this. First of all, this C int, okay, for a VLSI designer, C external, what we connect depends on the functionality, right? So this is not that I decide, okay, this much will be my fan out. Fan out always C external will be decided by the circuit requirement. Okay, so this is not in my hands. Now if I have to, now depending on the value of C external, so the total capacitance will change out here. Now if I don't want the delay to be a function of C external, what can I do? I can increase the value of the W of this of the inverter, right? If I do that, if I increase the W, then C int will become high as compared to C external. So, this term will come to 0 and the delay will keep decreasing and it will reach TPO. Okay. But again remember, increasing the size of the inverter W, right, WP and WN won't change TPO. Okay, it will only offset this C external, because now higher currents can flow. So, the external load water can get charged faster, but TPO that does not get changed. Okay, so with increasing S, you will find that the total delay is approaching TPO. Is it okay with all of you? Okay. Now there is an always by doing that. Okay. No, so is it advisable to keep the inverter size very large? Because it will also, you will have to take into consideration large capacitances will increase the power dissipation. The dynamic power consumption is going to get higher. Okay, because if you use C int large, then the penalty which you will have to pay will be higher power dissipation. So nothing comes free of cost. You need to remember that. Okay. Now suppose I have an load. Okay, CL. Okay, a large CL. Now should I use a single inverter to drive? I have an one inverter and I have some an external load, right, and a CL. Should I use a single inverter, or can I progressively have a chain of inverters so that the propagation delay is minimum? So how to go about deciding that aspect, we will see now. C int is the sum of all internal capacitance. Yes, C int is the sum of all internal capacitance. Now there is an C int is gamma CG. Okay, this is the proportionality factor. Okay, that depends on the technology, and it is close to 1 for most sub-micron process. Okay, that means the gate capacitance out here into gamma. Okay, that is the total C int. Now, if I go back here to my original circuit, which we showed here, right. So this is C int here, what I am speaking. C int is CGD and CGDP plus C D P with respect to the body. So these are 4 capacitances. Okay. Now these 4 capacitance is called as together in parallel is known as C internal. Right. Now this C internal we are saying it, okay, here as a function of gate capacitance of that particular, it is gamma, and for most technology in submicron process, this is close to 1. That is, the total net capacitance at the output node is equal to the gate capacitance. So now I write C TPO as C external divided by, instead of C internal, I am writing gamma CG. Right. Now if you see here, this ratio CG, right, by C external by CG, I am calling it as F. Okay, F, right, small f. So I replace it by small f here. Right. Now if I have n stages out here, at any stage, okay, what will be the delay of this particular stage? It will be TPO plus 1 plus the output capacitance divided by the input capacitance, right, CG and C J plus 1, because that is the gate capacitance of the next stage, right. So that this is going to be the load capacitance is nothing but the gate capacitance of the next stage. So I can write CG J plus 1, and here it will be gamma CG, right. So is this equation clear to all of you? Okay, so it becomes TP0 1 plus Fj by gamma. So this equation is, now the total delay for this inverter change will be sum total of this. So you have to for each stage you can do a summation out here, right. Now let's do a little bit mathematics on it and try to find out. Now suppose I have CG here. Okay, this is the input capacitance of an inverter, and the CL, this is the final load which I need to drive. Okay, this CL comes from the fan out requirement. Okay, now suppose I have made an inverter, I have to give that particular signal. This could be a clock signal also. I need to drive say 10 flip flops, so that value of CL will come from the circuit requirement. Okay, so suppose a circuit requirement is CL, whereas my inverter gate capacitance is CN, which is known to me. Right now, I have to drive this CL with an inverter. Now, is it wise to make use of a single big inverter or a chain of inverters? That we are going to see here. So let's define. Suppose so I am using a chain of inverters, and geometrically they have been sized. Okay, that means W here is, if it is an 400, the W here will be 800, the W here, the next will be, right, geometrically progressing square of that. Okay, it is going like that, right? So that is why it is known as geometrically progressing a chain. If we have, then okay, this small f is nothing but CL by CG, right? CL by CG, and if you have an n number of states, yeah, yeah, tell me.
So one question over here. So basically over here we have, I mean, n, I mean the subsequent fan out.
Yeah,
Basically, we're considering that the n is basically creating another fan out port, right?
correct,
But over here, the 2 is already a fan out with 1. So there will be a CL corresponding to according to for 1, right? So
correct.
that for the propagation of propagation delay of 1 of the, can we consider that part in this case?
Yeah, yeah, we are going to consider that. Okay, we are assuming that the sizes are, as of now we are considering that from here to here, here to here. Okay, they are geometrically progressing. So that is why we are writing it as an f for each. This is for f. Small f is the small f is for each of these from here to here. Okay, this small f, this total f is given by CL divided by CG, and if you take an because there are n stages out here, so I take for the small f, I take an root n out here, right? So the f, the total right effective fan out is CL divided by CG, right, and I have n different stages out here. So the fan out per stage will be n divide root of n by f, because this is size geometrically. Okay, it is okay. So this becomes an
But actually, over here, I think we have not considered the CL between the 1 and 2 and subsequent stage, right?
no, we have considered that, right? So if you see here, right, Cg plus 1 divided by Cg, right, and this f is kept constant everywhere.
Okay, so basically we have assumed that the bias capacitance and the input basically external capacitance of each of these stages are similar. That is,
Yeah, yeah. See, the delay. Okay, the if you see here, the delay, right, is proportional to f, right, and f is what, the ratio of the output gate divided by the input gate capacitance, right? So if you see here, the delay of each stage, the delay of every stage is C j plus 1 divided by, if you okay, so we are keeping f constant for each stage, right? Okay, we are keeping the f constant for each of these states. How are we keeping the f constant? Because Cg divided by Cj plus 1 divided by Cg, we are keeping it constant by increasing the signs in a geometrical fashion. Okay, so the small f is given by root n by f, right? So for so the delay of one stage will be given by TPO into 1 plus root f by gamma from here. This small f,
where the f is constant
f
and
is
f, which is basically assuming
correct, correct, right. Okay, now that is the delay for one particular stage. Then you go to multiply it with n, okay, to get the total delay here. So this is the equation which we get out here, right. This is going to be the total delay, right. Now if you see here, what should be the value of n now here, right. This we know, this is comes from the load requirement, this we know, okay, this is the inverter gate capacitance. What is variable out here is n, how many number of transistors we should have, okay, that is a variable here, right. So what I do is I differentiate this equation with respect to n. Here if I see here, the only variable out here is capital N, right, where all other things are constant here. So if I differentiate it and if for gamma equal to 1, okay, this is the typical case. If I for gamma is equal to 0, I will get the value of n, and once you get the value of n, you can compute the value of small f. So I will get it for gamma is equal to 1, and I get f is equal to 3.6. Okay, so this is the optimum value of f for which the delay will be the minimum. Okay, so this equation, if I differentiate it with n and equate it with 0, so I get the value of right, the value of n. So if you see here, now if that is being equated to 0, so I get a small f to be as 3.6 here. That means if you see here f, so for 3.6 value of small f to be 3.6, the delays will be almost minimum out here. Okay. So when I make a chain of this, this example will make things very clear. Suppose capital F is 64, right. What is capital F 64? That means I have a load of say 64 femtofarad. Okay, why is this load 64 femtofarad? Because probably I have to use, suppose this is a clock out here. Okay, I have to make a buffer in between, an inverting buffer out here. The gate capacitance is 1 femtofarad here, whereas I have to say drive n number of flip flops, say 8 flip flops, and each flip flop is 8 femtofarad. So the load is very high, 64. So what do I do? So can I use a single inverter or 2 inverters, 3 inverters, 4 inverters? Okay, so how to go about it? So if I use an f is equal to, right, n equal to 1 out here, right. So if I get an f is equal to 64, and the propagation delay, this is a computed value, so we are getting around 65. This is for certain, this is from I guess Rabe's book, where he had done some simulation results. So these are some simulation results. So he got it as 65 picoseconds out here. Now if we had used 2 n is equal to 2, that is 2 gates, 2 inverters cascade, then f comes out to be now 8, right. So because it is an 8 and then one more 8, 64, right. So this is geometrically progressing. One, like if I use a 400 nanometer and 800 nanometer, here it will be the Nmos will be 8 times first, right. Here you will have to use straight away, like if 400, if it is the minimum size, into 64, that much Nmos, and Pmos will be twice of that, right. So let's talk only about Nmos sizing. Pmos is considered to be double of that. In this case, if I use a 400 here, then I have to use into 8 times out here this inverter. So right, so this is how. So if you because so 8 times the Nmos, so f becomes an 8 out here. So these stages have to be scaled up geometrically. Okay, so if I use that, then he observed that the delay is around 18. And now when he used 3, okay, that is n is equal to 3, then f comes out to be around 4 in this particular case, and the delay is around 15. Right, that again if you are increasing n, then f again comes below that, but again the delay start increasing. So when you have to have a chain of inverters, okay, so we have to keep f, the small f, close to be 4. Okay, so it can be kept around 3.5 or 4, so that you ensure that the delay is minimum. So whenever there is a large load, it is not that we will use a single transistor and make a huge transistor to cater for the to bring down the delay. So the better option would be to use an chain of inverters with geometrical sizing here, and one transistor, one inverter having an small f, each of these inverters having a factor of f. That means the load capacitance out here should be 4 times the gate capacitance out here, right? And how can we ensure that? By accordingly sizing the transistors. If it is 400, NMOS size is 400 out here, in the next stage you have to keep the NMOS size as 1600 nanometer, 400 nanometer, 1600 nanometer, and then again 4 times the size of the so width you will have to keep increasing in an geometrical progression manner. Okay, so this is what when we have.
One question.
Yeah, ask me.
In order to make the, basically we are doing it to make the propagation delay to be minimum.
Correct, correct,
Now, for this sizing has to be made. Now,
correct.
if for a single digital IC,
Yeah,
everything would be mapped onto a single wafer, and single same nanometer technology is normally used, right?
yeah,
So
correct.
for sizing different gates with different width, is it not like cumbersome from the fabrication technology?
No, 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 no. Yeah, the generally, okay, W by L is an parameter which is available for a VLSI designer. Any circuit for that matter, we will see that W is an thing which can be easily changed. There is no problem at all in having variable W and L also for that matter. But in most digital circuits, we do keep an L constant, okay, because the layout becomes simplified, but W is not at all an issue. Okay, so in the next class we will see how to make certain layouts of circuits also there, and stick diagrams and things like that. We will see that W is a variable. In analog circuits, even L we do change. In digital circuits, L we keep constant. But in the advanced VLSI course also, you will see you will have to change W in many cases for the circuit to function at all. Okay, you will have to make certain parts of the circuit. When we see SRAM also, we will see that W is a variable which will be it's a variable, and a variable which needs to be changed for optimizing the circuits. Okay.
Sir,
Yeah.
one thing.
Yeah.
Okay, so first question is that I mean this if it is an inverter, right? So
Uh,
we have to consider the functionality also, right? So
correct.
because I think I mean if we are having three back-to-back inverters, then the functionality
Correct.
will not be maintained, right?
Correct. Correct.
That is one thing, and the second part is that over here we have considered that the I mean these CL values are for the each and every stages are different, but actually it will differ because now we are driving the smaller guy is driving the bigger guy, so we have not considered that part over there, right?
Yeah, that we are assuming that yeah, if you see here, here the CL is slightly it would be modified, but
So the 2.8 is now driving the
yeah, correct. And yeah, I got your point. Obviously, here you will find CL is coming from this transistor also. Here it is not coming, so that aspect has been neglected. Yeah, yeah.
and this propagation delay so is for the complete from basically the complete chain, right?
Yeah, from here to here. Yeah, yeah.
Okay.
So
And how this formulation was happened?
I think normal sizing of the inverters. This in fact in cadence for the on-campus students, we did it in our lab also using 180 nanometer, taking the same values. So they also you can also do the same thing. I'm not sure in LT Spice whether you are going to get similar results, but you can try that. You can take a big capacitance and do this simulation even for 180 nanometer and check. So somewhere around if you have these values, you will get the least propagation delay. Okay, so it would appear as if you are making a 3 inverter, there will be 3 inverter delay here. That is not the case actually. Okay, so obviously this will take larger area, but that it will give minimum delay. So no, if you just make a cursory glance, it would appear there are 3 inverter delays here, but that is not the case actually. Yeah. Dhanbal, the size factor will be 4. Yeah, that is what. So we have to keep the size factor 4. Number of stages. Now, if you take the size factor as 4, number of stages will depend on the ratio of the final CL divided by CG.
So
Right?
actually, from this, I think all the values, I think is clear, but this part is not clear. That the subsequent stages, right? The 2.8 to 22.6. How this was decided that the sizes of the subsequent. Oh, okay.
Okay, that is from this 2.8 F what you got, right? This total F was fixed initially.
The last slide before this,
Yeah,
the other one before this, right?
yeah.
Okay, so effective fan out is 3.6.
Yeah,
That is the best one.
that is the best one.
Okay,
Small f.
fan out is a okay,
No,
okay.
this is not kind of this stage.
This is for each stage. For each stage, okay, C external divided by C intrinsic should be 3.6. C assuming C intrinsic.
Would not be an integer, right?
Yeah, n may not be an integer for that case. So you will have when you do the approximations, you will whatever is the closest you will get, right? So you will have to do that. Whatever is coming close to 4. When you divide CL by C intrinsic, no. So whatever you get closest to this figure. So either we fix this and take the closest or whatever. So a little bit decimals you will have to adjust. Right? Is it okay? Okay, so we'll this is okay. Short circuit. This we studied, right? I had this we already covered in the class 1. Yeah, 4 is taken as an optimal. During this I had included because since we are doing transient analysis, so this we saw when the input is switching from 0 to 1, there will be some short when both these transistors will be on for a certain duration. This we saw in the very first class, and then we also saw that if the load capacitance is kept high, then the short circuit current will not be that much. Okay. This we studied in detail in the first class, and then we also saw the switching loss formulas. This also, right? I have just put these slides out here so that this topic remains complete. With this, we have discussed in detail in the first class. Okay, now this is known as an ring oscillator. Why I have put it here is because whenever a new technology is proposed, the Fab Lab generally they will give this kind of circuit, okay, the performance, okay, here, right, because the frequency of operation of this indicates the total on currents and the capacitances. Like when I say a device is good, right, for digital application, that means it should have higher ion and lower CG, correct? Isn't it so? Right? If I am comparing two families of devices, right, a device will be better if it has got higher ion and lower CG. So ion by CG ratio is the actual thing which defines the overall performance, right? So if you say power, speed, everything, so I on by CG ratio, okay, that should be as high as possible, or sometimes it is referred to the CG by I ratio, okay, which is an no, CG by I is the delay portion of it. So generally the technology guys, okay, when a new device is fabricated, so instead of defining CG and I, they give these kind of curves, okay. So this is like if you have an inverters and it is connected in a chain out here, right? The frequency, higher the frequency means, okay, if the once you have given higher the frequency means, okay, what is the frequency which you are getting? So that will be specified by, like for a 45 nanometer, when you do this particular simulation, you will get one frequency. For a 22 nanometer, you will get a different frequency. For a FinFET technology, you will get a different frequency. And this particular frequency what you get indicates that there is lesser propagation delays. That means I on to CG ratio is better. Okay, so this is the this is one of the figure of merits which you will find this particular circuit, and this graph you will find whenever a new technology is released. You will find in the specifications this particular graph you will find, chain of inverter graph, right? So and the frequency will is given for specified for various frequencies. Higher the frequency, that means it would operate in a much faster. Okay, is it okay? Yeah, yeah.
If I talk about the inverter, so at for inverter one, there is at the output, it has like the P load one is
No, intrinsic. We don't put these loads out here, right? Okay. You make a chain of inverters and you calibrate this, and then you publish this result also along with your technology data, so that the user knows, okay, this defines the actual performance of these devices in an actual circuit when we are designing. So this frequency will, yeah.
these are all identical and actually it is equivalent to the CG.
Yeah. Okay. Here it is not geometrically sized. Okay. They are all same size inverters, 3 inverters which are coupled. Okay. This is from a data sheet. This is just from a snapshot from a data sheet of an technology file. Okay. Yeah. Tell me. You are telling something. Okay.
For this, all the capacitances are same, right?
All the capacitances are same. Identical inverters connected. Okay.
But this is equal to the CG for each of the inverter.
Yeah, it is equivalent to CG, right? So this is yeah.
Basically, what does this curve signify? Actually, I'm not able to.
See, whenever a new technology, somebody is proposing a new technology, some new device, right? In the technology file, along there will be lot of data which will be available, CG, VT, and all. Okay, but for a digital designer, this particular waveform, which is shown in that particular set of data which is published, this is one of the most important performance plots.
It basically tries to signifies that there, if there is back-to-back inverters, so these are the propagation delay, and the propagation delay are remaining constant. Like, is that
No,
signifies this?
no. The
This is a basic stable multi-inverter kind of a circuit,
yeah.
and it will be like an oscillation period which will be determined by the propagation delay of
Correct. See, if these three, say I have a 45 nanometer technology device, and I have made a chain of 3 inverters, and I am getting 1 gigahertz frequency, right? If somebody else is again coming up with some other technology, and if he is putting these 3 capacitances like this and doing the same results, and he is getting a frequency of 2 gigahertz, right, for the same set, that means his device is superior. Okay, why is it superior?
the additional number. Right.
Yeah,
But then, got it. So basically, then this is okay. So this is basically the delay of these guys.
yeah.
But actually, this is I mean,
This is a figure of merit. This is a figure of merit for this particular set of devices, for this technology device. Okay, this because all those, so many, there will be many parameters and a VTH, body bias, those things for a designer and for a VLSI engineer and like us and who are not very much keen on physics and all. For us, and those parameters are not very important. This is what the key performance result for me, right? Because
total delay of these. I mean, if there's a back to back, then what is the total delay and how much frequency it can offer?
correct, because this is dependent on the I on and the capacitance, I on divided by CG ratio, right? When I'm moving from one technology to other, if I simply increase I on by increasing gate capacitance, then it is of no use to me actually, right? So when I am moving from one technology to other, I have to increase I on to CG ratio. Only then the performance will be better, right? So that gets characterized here, and for a circuit designer, this is an important figure, right? If I get this frequency higher, that means ultimately when I design a circuit, it would be better for me, it would operate faster, right? Okay. Okay, thanks a lot. In the next class, we will take up an static design, CMOS static design, and followed by it, actually it is a spare class, but instead of an spare, I would spend some time talking about stick diagrams and Euler's theorem and all, because somebody had in a few days back had requested for stick diagram, although they are not on a portion of the theory prescribed syllabus, but then we will see how to make an optimized layout. Okay, those issues we will discuss next class. Next class we will tackle static design. Okay, thanks a lot.